what we are trying to do is we need to address all the spectrum of research from the basic fundamental research. Partnership with the NEET Education Research Institution, all the way going to truly an accelerator in the country, as the Qatar Science and Technology Park, and more recently, what you probably have heard about, are a set of world-class research institutes that are the result of the honest initiative from how to bring the Arab scientists from around the globe to contribute with us and to work with us through the development of science and research in the world. Another equally important element in our research landscape here is the Academic Medical Center that is that is due to open within the next few months, and that's again another hallmark of the Qatar interest and objective in developing world-class health and research. Now, the most important of all of those is, of course, like all of you know, from your own experience in your own institutions and countries, that without real sustainability and the strong commitment at the national level, the leadership level, it is exciting for development at last. So we do have that, and it's truly a commitment of 2.8% of the national GDP to support research and development. I'm sharing with you very briefly some highlights on how that research and development landscape in Qatar is now leading to a very exciting therapy research environment. Now, we want to go to the next level, which is not simply enabling research, but also how to build it, implement it on the ground, sustain it for the long term. So, I will focus just for the sake of time, two sets of programs that we have at Research Institute, and we are fortunate to have met yesterday with a number of our scientists coming from around the globe to share with us this excitement, but also to get involved with us in building this program. The really one key issue that is all our heart is how best to build capacity in research and development. And we have set up a truly innovative research training program called Science Leadership Program, and a brilliant lady who introduced me just a few minutes ago is really one of the members of that program, which is now pursuing her PhD in UK, and we're counting on her to come back sometime soon. There is no doubt that you have already understood that at the heart of the research and development model that the Qatar Foundation is choosing is the influence and partnership with elite institutions around the globe. So we are looking into expanding the program of that approach for further development of the research landscape in Qatar Foundation. Of course, I cannot talk only about what has been done, but also what we hope to achieve for the short term and also the long term. So as you can see, these are a few areas that I'm not going to go into the detail of any of them, but I think you can already notice there that we have a broad interest, yet very focused in each one of them, starting from the biomedical, the energy and environment, and computing, where we have truly structures now, real structures on the ground, but also we don't forget about the social sciences, the behavioral sciences, the art, and the sport, of course, that also part of building this recharging landscape of research and development, and for the society as a whole. Now, we hope, of course, for the short, for the medium term, to position Qatar as not simply using science products or development that has been done somewhere else, but also to innovate itself, even at the regional level for the short term, and hopefully also at the international global scene. Now, I of course cannot resist but sharing with you some of those figures that we have for this annual research program of 2011, and just to remind you that the last year forum we had about 500 participants, and now we have almost three times more. Also, equal impressive number of institutions from the country and also internationally, a number of institutions that have collaborated with us or working with us at a different level. It is important also, as Dr. Wafa has mentioned, there will be presentations tomorrow after thereafter from our scientists and students, and the number of leaders that you see in front of you is truly very impressive. Students are also eager to participate, and they have been extremely incredible. And actually, they are not given a choice, because they will be a wide set of extremely high-level, really scientific experts. So, now to take you to what is going to happen within the next couple of hours. The very first meeting will be Panel 1, and that will be dedicated to the globalization of research in the 21st century. And the whole idea behind it, as has been already announced and highlighted by the Highness during the last year forum, is how best to not only to build new knowledge, but also how best to share it with the rest of the globe, in particular those who may be less fortunate in having access to the real-time and timely scientific information. And we are assembling for that panel really science leaders from around the world, including also our own science leaders from Qatar, so that we can and come up with few suggestions on how best Qatar Foundation can endorse some of those that we will later on implement. After the show, there will be the second panel, and I think you will immediately realize the importance of that second panel. You cannot talk about globalization of research without also taking into consideration that some of the knowledge that is being related to globalization started can also have an impact, an immediate impact on society and on the economy. And that panel will address some examples on how to achieve that. Of course, I should not forget to mention those who have believed also on the importance of science, research and development in contributing to society and economic development. Some of them have already been with us last year, and others are joining us now, such as the ExxonMobil, Total, Chevron, Shell, as well as other partners in scientific publication, such as Pure Science, as well as New York Academy of Science. And of course, importantly also one of our education city partners, Kennedy University of Qatar. With that, I wish you really a very enjoyable 2 panels. I will now call on the members of the panel.
Assalamu alaikum. Thank you so much for the kind invitation to come here and visit with you today. I'm very excited to have the opportunity to talk with you a little bit about some of the research that is going on at Berkeley Lab, but also very much to talk with you about our vision for what research is going to be looking like in the coming years, and start a dialogue with you about ways in which we can interact with each other in the years ahead. So the topics that I will discuss this morning will concern a little bit, since you're discussing the issues of the vision for what the Research Foundation, Hathor Foundation, will be looking like in science here, will be looking like in 2030. I thought it would be interesting to start our discussion by trying to ask how will science itself broadly internationally evolve as we head towards the year 2030. And of course, that's always a very tricky business because we tend to be influenced by what we see at the moment, but nonetheless we try to project out to the future. And also we have to ask what extra demands will society have from science as we go forward. Society always has many needs from science, but as we look towards future decades, there will be even stronger needs that society will place on the world of science, and we need to try to organize ourselves in a way that is responsive to those. So let me say that as we think about science itself, we can imagine that we need to start from a foundation of the very fundamental sciences, such as mathematics, physics, chemistry, and biology. Those are, of course, the core disciplines from which everything else that we can do in science is ultimately built. And then, as we try to project out what things will look like in the coming decades, there are three new pillars that are being built today, and which will be mature by 2030 probably. And so the first one is the field of nanoscience, in which we learn to control matter on very small length scales in completely new ways. And I think we can predict with some pretty good confidence that nanoscience will lead us to have the ability to create highly advanced materials and highly intricate design systems. I'll try to give you an example of that as we go forward. The second large megatrend, if you like, which is a pillar for science in the coming decades, will be, of course, the biological sciences themselves. If we step back and look at all of science today, all of what we see in the world of science today, there is one area that stands out as kind of the central pillar because it's changing so comprehensively, and that's the field of biology. Biology today is entering an era where it is much more quantitative rather than qualitative. It's no longer a descriptive science. It's becoming a science in which there are hard laws that are helping us to organize and understand the information, and it's becoming also potentially a tool for the creation of things, as opposed to an area in which we are more observational and trying to understand what's there. For example, we could imagine in the decades ahead that we might be using bacteria that are specially designed and modified in order to make the chemicals which today are made using petroleum, and that would be a major development that could emerge only as the field of biology continues to emerge. So nanoscience, biology, and the third pillar that I would call out would certainly be computation. Computation itself has increasingly become stabilized as the important third leg of science, the ability to simulate things, but it appears to be entering a qualitatively new era in which actually almost any project in science cannot be completed without computation being a critical piece of it. And we see the field of computation itself dramatically changing by the development of the ability to collect massive data sets. At Berkeley Lab, we are helping to maintain the ESNet network that the Department of Energy runs in order to pass data sets around the world. And it is not uncommon today to have petabyte data sets traveling across the world, and the handling of data of that scope and scale is a fascinating topic that is going to transform the ways in which science is performed. So we can see here nanoscience, the ability to purposefully create matter that is highly designed, biology, the ability to understand and manipulate the living world around us, and computation. Those three will be pillars of science in 2030 in important ways, and as we plan our future, we need to take that into account. Now, as I mentioned to you, we need to think to what end will all of these things be occurring. And as we look at the world around us today, I think one thing that we can be quite confident is that there will be a major and increasing trend where science will be called upon to help deal with immense and large-scale problems of energy and environment. For sure, in 2030, there will be issues of health, there will be issues of all the other issues that science addresses today will still be there. But the energy and environment issues are going to grow in their importance in quite remarkable and important ways, and we can predict that from many factors that we'll be looking at momentarily. So what I see is that this pillars will increasingly be called upon to support research that tackles problems in energy and environment. That's the landscape that we see in the decades ahead. Now, how did we get there? I'd like to show you this iconic photograph of the start of the national laboratory that I'm the director of. This is E.O. Lawrence, who came to Berkeley to start his research career, and soon afterwards invented the cyclotron. And when E.O. Lawrence invented the cyclotron, he very quickly had a key insight, which has had impact far beyond even his physics discoveries, which were, of course, quite remarkable. He had the insight that in order for him to realize the full potential of his discovery, he needed to work with many, many other scientists and create a team. And in many ways, I would say it was probably the first example of true team science that developed in the world. So one thing about his philosophy, as you can see in this photo, he has all of his early career colleagues here. A few of these here won Nobel Prizes later. You can see here all of the staff that were supporting. You can see the incredible absence of diversity in that era. So all of those things are present in these photographs. But one thing to remember about it is it shows the tension. It shows the tension between the creative individual and the team. And that, of course, is what a lot of modern science is all about. Now, the lab that he founded did go on to grow substantially, and today it sits in the hills above the Berkeley campus in a beautiful spot in Berkeley. And I would like to invite everybody here at one occasion or another. We would very much like to have you sometime come and see what Berkeley Laboratory is like, because it's a very special place. It has about 4,000 employees, a budget today of about $730 million a year, and many national facilities. And I want to emphasize that because in order to accomplish our research agenda today, scientists need to come together in teams and establish large-scale facilities which are far beyond the abilities of any individual researcher to ever create. And that is a key piece of what science looks like today. In fact, this ethos of strong individuals creating robust teams is the basis of a lot of modern science. And it has worked well for Lawrence Berkeley National Lab. There have been 12 employees who have won the Nobel Prize, and about 3% of the United States National Academy of Sciences on the staff at this laboratory. And I really attribute the success of the lab over its many decades to having gotten write this formula for how to approach the topic of team building and individual creativity. One other megatrend, of course, which I think everyone here is quite well aware of, is the topic of globalization and the fact that there's really only one science, and science increasingly spills across all borders. There are many efforts to try to describe this, by the way. This shows a map which was created by simply overlaying every time two authors publish a paper together, drawing a line. And so you can see some of the lines that have been drawn for all of the collaborations that are occurring. And if you make a map of that as a function of the time, you can see that the lines across the continents are getting stronger and stronger as time goes on. This is a type of map which scientists are increasingly trying to create. This, for example, shows chemistry and physics is over here, and some of the social sciences. This is an effort to try to make a map of all of the disciplines of science and how they connect with each other. And again, if you draw those as a function of the time, what you see is the increasing networking that is occurring. So we know that cutting-edge science today requires teams that work across many scientific disciplines, and international teams are now the norm. They're not exceptions anymore. They're becoming the norm for how science works. Global connectivity enhances cooperation, and especially gives competitive advantage to those who embrace it. If you work with trying to create worldwide teams, you will be more successful in your science and have better opportunities. But of course, I emphasize again, part of that needs to be fostering creative individuals. And I want to also state that the way that happens is not automatic, but happens through intensive personal mentorship that can often occur globally across continents. And so this issue of global mentorship is really very front and center. One last point on this: society is more dependent upon science every day that passes, and yet large parts of the science, large parts of the population in the world are very remote from science. Some are even alienated from it and are distrustful of science, and that creates a very difficult stress situation for science and for society both. So public science education is something every science institution has to embrace and work on very hard. Okay, so now I'm going to go through briefly the Carbon Cycle 2.0 initiative. I think that you all know that if we look at the carbon cycle itself, in its state when there's not a lot of anthropogenic or human activity, processes, short-term ones, which might involve, for example, the biosphere, which exchanges carbon with the atmosphere very quickly, and the much longer-term geological one, in which we have volcanism creating CO2 into the atmosphere when there's a volcano, which ultimately leads to sedimentation and subduction and creation. That cycle, that ultimate geological cycle, is the one that determines the long-term carbon flux through the world. The biological cycle is very fast and is actually typically in equilibrium. That's the state of a natural configuration. Today, of course, we're, for the first time in human history, we've entered the stage where the actions of people are able to globally change the flux of energy, chemicals, and matter through the planet. And that's first manifested by this imbalance in the carbon cycle because of the fact that we take fossil fuels and burn them on a massive scale, as well as changes in land use. The combination of those two have resulted in a situation where we have created an extra amount of carbon put into the atmosphere every year that's in the number, 8.5 gigatons per year are the anthropogenic carbon emissions, but about half of that remains in the atmosphere each year. And of course, that is something for us to really think deeply about. And if we think about what's happening today, this is the total amount of energy production per year. If we think about what's going to happen as the global population increases, we're going to need in the future a few times at least by the year 2100, a few times at least more energy. And yet, if we are ever to bring the carbon cycle back into balance, we're going to need to make the carbon emissions at least 3 times smaller. So that means that we have almost a factor of 10 in how much we have to improve our ability to get energy per unit of carbon that we work with. That's a grand challenge for us over the coming decades. And it's this is one of the great challenges that all of the disciplines of science will be trying to address in the coming decades. So it's a huge challenge. And it shows that we need to go from this open-ended, unbalanced carbon cycle to a future carbon cycle 2.0 if you like, which is fully balanced. So at the lab, we have an overall program which we call the Carbon Cycle 2.0 initiative, which seeks to bring together all the scientists at Berkeley Lab, and it's probably over 1,000 of them, who are working on one aspect or another that relates to the problem of the carbon cycle. And this diagram is intended to show how all of those different science projects are connected to each other. What you see on it is this circle in the outer region and then the central region. In the central region is energy analysis and climate modeling, and in this outer region here, you can see this is what I would call the arc of carbon. You can see here combustion, capture and sequestration, biofuels, artificial photosynthesis. This is how we use carbon today. This is what we will probably need to do in the short term. Biofuels will provide us some relief, and then ultimately 30 and 40 years from now, we may well be doing artificial photosynthesis. So that's the future of carbon technology. On this side of the diagram, you see the off-ramps. Instead of using carbon, we stop using carbon through efficiency, increased use of solars for electricity, and other forms of energy storage. And the developing world I'll mention in a little bit. Now, each one of these circles represents a significant research program at the laboratory, and in the center sits this group that does energy analysis, whom we ask to go and talk to every one of these groups and provide a common economic analysis and resource analysis and a scoping. How large can your research effort ultimately be to impact the future of the carbon cycle? And then finally, those energy analyses flow naturally into climate models, which are being developed now and which operate on a regional basis to say, okay, if we deploy, for example, 60 million acres of solar in the Nevada desert, what impact will that have on regional climate when you turn the tan-colored desert to a black-colored solar on that scale? So there's many aspects of this that all come together in an integrated point of view. To illustrate that, I'm going to look at one example this morning, carbon capture and sequestration, and then I'm going to touch very briefly on artificial photosynthesis and developing world, and then I'll stop. So let me just show you briefly the story of carbon capture and sequestration research at Berkeley Lab. It's one example that you can see the idea of this diagram in action. First of all, the problem, of course, I think you know, we emit approximately 30 gigatons of CO2 per year, and it's very hard to understand what that number means. But here I show the top 100 commodity chemicals produced in the world. So these are all of the chemicals that are produced in vast quantities, such that you might transport them with giant trucks and cars and so on, and all 100 put together amount to half a gigaton, compared to the 30 gigatons of CO2. This gives you a feeling for how big this is. It's 60 times bigger than the top 100 chemicals all put together. So naturally, this scale of the problem means that in the end, we will still be using carbon-based fuels in 2030, 2040, and 2050. There's no doubt about it, because we don't have the ability to transfer to any other technology on that time scale. That means that capture and sequestration is one of the possibilities that we have to very, very seriously evaluate. And unfortunately, the technology that we have today is a rather poor one. What you can do is capture CO2 from the flue gas from a power plant by bubbling it through a solution of water containing amines. The amines bind to the CO2 and pull it out. Now you might say, why don't you just leave it there? Well, you can't. To capture all of the CO2, you can see the top 100 chemicals are only 1/60th of the amount of CO2 that's produced. That means that to capture CO2 effectively, you have to transfer it. You have to first capture it and then release it somewhere. And that somewhere has to be big enough to keep it. That's why you have to capture it and then put it underground, almost certainly. And the current amine process is very energy intensive, because at the end, that CO2 binding is quite strong. But to release the CO2, which is a necessary step, you have to boil the water, which of course consumes a tremendous amount of energy. So approximately 25% of the power of the power plant is required simply to capture and then release the CO2, which is an unacceptable amount of extra energy and far from the thermodynamic limit of what could be achieved. Therefore, we turn to our scientists at the lab and at the world at large and ask, isn't it possible for us to create a better way of capturing the CO2? So this is where advanced materials discovery becomes very important. Today, Omar Yaghi is here in the audience. He's the discoverer or developer of the class of new compounds called metal organic frameworks, in which inorganic and organic species are combined in intricate new ways. And here you can see a picture of a so-called metal organic framework. I think this is a very beautiful picture of the intricate structure that has been created recently, which is essentially a solid-state version of highly porous material that presents amine functionalities that can bind the CO2 in very selective ways. But now it's solid-state. There's no water. When you capture the CO2, you can warm it up gently and release the CO2. This is made out of elements which are abundant and which can be readily used to bind the CO2. So it looks like there's a real possibility. It's still early research. This is some work from my colleague Jeff Long at the Berkeley Lab, who has shown some remarkable characteristics for this particular metal organic framework, which in fact does use approximately 1/3 of the energy of the current amine-based solution. So that's a big breakthrough, and I think we're going to see many others like it. I want to point out to you that this breakthrough does not come from a vacuum. It comes from many years of studying the fundamental chemistry and material science and even physics of this class of material. And now that material can be designed in order to be used for this important societal application. Likewise, we can see that systematic control of these materials allows us to create many other very beautiful symmetries and arrangements. And here from some other work that Jeff has done recently, you can see another metal organic framework, which is being used to separate a mixture of alkanes, which, as you know, in the petroleum industry is a very key thing to be able to do and quite difficult to do. Again, here we've got a system which has been designed that has the ability to do this in very selective and interesting ways, and it saves energy quite a bit. And it's only one example of how the creation of new materials will enable a wide range of new energy technologies. Once the carbon is captured, it has to be sequestered, and in order to do that, we need to understand the risks. People are fearful that if we take CO2 and put it underground into a reservoir, that the CO2 could escape again. So we need to have monitoring of the outside of the reservoir. We need to make sure that the seal is robust. But most importantly, we need to really understand at a very deep level what happens when you stick CO2 underground and it mixes in with water. What is the phase diagram? How does it mix? What's the nature of the reaction of CO2 that's in this complex fluid as it reacts with mineral surfaces? These are deep questions that involve physics, chemistry, and geology mixing together disciplines in a very interesting way. So the challenge here, of course, is to simulate on the computer the long-term fate of carbon dioxide injected underground on length scales that vary from nanometers to kilometers. This is a terrifically challenging problem that faces our science today. Here you can see some recent simulations from the laboratory. On the one scale here you see at the nanometer scale, this is a tiny pore in the computer. This is a quartz tube, if you like, in which at the computer we have water and CO2, and we can study the nature of the interaction between those two as well as any reactions with the interface that might occur. This generates kind of microscopic scale information, which then we try to verify by specific experiments that study the surface interactions in the laboratory. But then this data informs ultimately what goes into a set of simulations. Here you can see simulations of CO2 being injected into 20 wells in an area called the Mount Simon Formation in Illinois. This is an area where there are a lot of power plants that generate CO2, and nearby there's an excellent geological formation for storing the CO2. So on the computer, they have injected CO2 into 20 locations over a period of 50 years on the computer. They've injected 5 gigatons of CO2, so it's a noticeable amount, and then they've simulated it for 200 years after that. And they find that in this case, for example, the CO2 does not spread from one site to another over that time scale, but it does, as time goes on, burrow down deeper and deeper into the region. And they find that the pressure goes up quite a bit, as high as 30 bar, and that's because there's briny water in this formation, and when you push the CO2 in there, it just basically raises the pressure a lot. This is now where our project takes an interesting turn, because we've gone from creating a capture material to doing the simulation experiments, and now we turn to our energy analysis group at the laboratory. These are economists, a few social scientists, and others, and we ask them, what do you think about all this that we're doing? Take a look at the science, and what do you see? And they turn around immediately and say, you know what, all that extra pressure that you made inside there actually could be used simply to push the brine out of those pores and create briny water. If we create the briny water and we can separate the water itself and collect it, and also collect the salt. And the salt, for example, from this Mount Simon Formation, could then be sold in the Midwest for road salt to help melt the snow when it's snowing. So there's an economic use for it. And when they calculate that out, they find that they could probably get approximately $17 per ton of CO2. Compared to the $80 per ton of CO2 for the capture, that's a significant number. So it shows that there's probably an integrated way of making this technology be used in many interesting ways. In fact, if they do a complete life cycle analysis, you can capture a great deal of value from the brine in the water. CO2 from a 1 gigawatt coal-fired power plant could displace 20 million meters cubed of brine per year. And it turns out that if you act on it by doing some geothermal cycles with the CO2, use the CO2 as a working fluid for geothermal, but also push out some of the briny water, do reverse osmosis, you can ultimately collect the salt, and when all is said and done, you can reduce the cost of carbon capture by up to 30% by this collective complete life cycle use. And in the meantime, you get 50 gallons of reclaimed water per ton of CO2. So indeed, the CO2 problem can be connected back in with the water in this interesting way. This is an illustration of the idea behind this diagram. But imagine that taking place for every one of these topics, biofuels, solar PV, and so on, in which we try to think in an integrated way how to make materials, how to understand their fundamental physics and chemistry, material science, but also their energy analysis and how to connect them into a climate model. That's a vision for what a national laboratory that is integrated in its approach is capable of doing. Just quickly, two more topics that I will show on here, which I think are very special for this audience to think about a little bit. One is artificial photosynthesis. I mentioned to you a moment ago that our view is that in the future, one day, we will be doing artificial photosynthesis as a means of making our fuel. The idea, of course, is to make fuel from sunlight. Instead of making electricity by shining light on a solar cell, we could directly make fuel, which is, of course, what nature does all the time. This is a grand challenge for science. If we look at how nature does it and we look at the photosynthetic membrane, it is an intricate, complex system of exquisite beauty, actually. And the question